Welcome students, we are back with another lesson. In this lesson we'll discuss the nuclear density. In nuclear density, we will give an estimate of the nuclear density. How much value you can assume the density of the nucleus will have. So what is the nuclear density? Nuclear density means how much mass of a nucleus reside or how much mass is distributed inside the nucleus per unit volume. This is known as your nuclear density. So in my last class I have showed that the nuclear volume depends only on the mass number. How many nucleons are there inside the nucleus? Can you see this volume, the size of the nucleus? It only depends on the mass number. As you can see in this picture, the more the size, the more will be the nuclear volume. The less the mass, the less will be the nuclear volume. So this is I've showed in my last class. So now consider a nucleus. Okay, inside the nucleus you have nucleons. Let it be a neutron, whether be a proton. Okay, for now just consider as a nucleon. Okay, doesn't matter whether it's a proton or a neutron. Now this nucleus has some mass number. Okay, the mass number means the total number of the nucleons. In our case 1, 2, 3, 4. The mass number is 4. This mass number is represented by A. Next, this capital R. R represents the radius of the nucleus. Okay, consider this nucleus like a liquid drop. Okay, like a spherical liquid drop. This spherical liquid drop has some radius which is represented with capital R. Fine. Now next is your small m. Now if you have nucleons, then each nucleon will have individual mass. Clear? So assume the nucleon to have a mass small m. So what is small m? Small m is the average mass of the individual nucleon. Okay, so this nucleon has mass small m, this one has a mass small m. Okay, doesn't matter whether it's proton or it's a neutron. Clear? So if the mass of the individual nucleon is given by m, okay, and there are in total how many nucleons? A number of nucleons, then what will be the total mass of the nucleus? The total mass of the nucleus can be given as the product of the individual mass multiplied by the total number of nucleons, the total number of particles here. So if the mass of the individual nucleons is small m and there are total A number of nucleons, so the total mass of this nucleus is given as the product of mass times mass number A. So what will be the volume of this nucleus? Just now I've said you can assume this nucleus like a spherical ball. Okay, and we know what is the volume of a spherical ball. It is 4/3 pi r cube. And in our last class we have derived the relation for the radius of the nucleus. The radius of the nucleus can be written as the r naught, which is a constant, multiplied by the cube root of the mass number A. Fine. So let us substitute this value of radius here. So if I substitute, I can write as 4/3 pi multiplied by r naught A to the power 3. Yeah. Now if I open this bracket, r naught will become r naught cube and a to the power 1/3 multiplied by a to the power 3. What it will be? It will become simply 1. Therefore my volume can be written as V equals to 4/3 times pi r cube multiplied with the mass number A. Fine. So the nuclear density is defined as the mass of nucleus upon the volume of nucleus. So the mass of the nucleus is given as Ma and the volume is given as 4/3 pi r naught cube multiplied with the mass number A. Fine. On further simplification, I can write this denominator 3. Okay, it will go to the numerator. this A and this A will get cancelled. So I can write the nuclear density rho nu 3m by 4 pi r naught cube. Clear? So here this is the formula for the nuclear density, where 3 is a constant, the average mass of the nucleon is also a constant, 4 is a constant, pi is a constant, r naught is also a constant, which I've showed in the last class. Therefore, if I write these values, let me write in the next slide. So here, your average mass is given as 1.6 times 10 to the power minus 27 kg, and the value of R naught is 1.2 femtometer, which is 1.2 times 10 to the power minus 15 meter. Fine. Now, one more thing. In this formula, what you see that your nuclear mass has all the constants in its formula. What does this mean? Here, if you see here, what happens? The mass number got cancelled. Can you see? Here the mass number got cancelled. So if I ask whether your nuclear density depends on the mass number, if this mass number got cancelled, see in this formula, do you see any mass number? No. So what will be the answer? No. The nuclear density does not depend upon the mass formula. So what does this mean? It means that the nuclear density is same for all the elements. Clear? This nuclear density is a constant and it is same for all the elements in the periodic table. And how much will be that constant value? To evaluate or to calculate, substitute these values. So you have 3 here. The average mass m is 1.6 times 10 to the power minus 27 kg. 4 is 4. Pi I can write as 3.14. And this r naught is a constant whose value is 1.2 times 10 to the power minus 15 meter, and there is a to the power 3. So if you calculate this value, you will get the nucleus density. So you will get 2.3 times 10 to the power 17 kg per meter cube. Fine. So your nuclear density is constant for all the elements and its value is 2.3 times 10 to the power 17 kg per meter cube. Okay. So that's it for today's class. Thank you. And if you have any confusion, please feel free to ask. I will re-explain it to you again. So again, thank you.